And the first thing is to pass around the roll sheet. So you guys can sign that. I think I forgot last Thursday. It's okay, sometimes I forget this kind of stuff. Okay, that's YouTube stuff. That's good. That's my pre and post condition stuff.
We get to learn loops today.
Loops. Pre and post condition. Prove your loop is going to behave correctly. I like
prove
proofs.
it by demonstrating it.
No, you cannot do that. You have to prove it.
Proof by demonstration is the best proof.
It proves in one case it will work. All right. Let's go ahead and get started. Are there any questions from last? Are there any questions from last Thursday? No questions? Yes.
Yeah, you told us how to create all these variables, but you didn't tell us how to.
No, not
them.
Variables. We never talked about
Not
variables.
variables.
There's no such thing
You
as
told us how to allocate
variables.
memory.
Yeah, we can
You never told us
allocate
how to
memory.
access it
So there's a
from
big difference,
a
okay?
mod L.
Okay, there's a big difference between a variable and a region of memory that you can allocate in assembly programming. Okay, in C you can say int I, as a global variable. And not only are you allocating 4 bytes, you're also telling the compiler a lot more than you can tell the assembler. Because you're telling the compiler I is an integer. Every time you say I equals something, let's say you say I equals quote B end quote. Okay? Now quote B quote will translate to the ASCII code of the lowercase character b. Okay? Which only need 1 byte to store. What happens when you say I equals quote B quote? Okay, in C you can do this, right? Int I, and then later on somewhere in the code you can say I equals quote B quote. What happens when you do this? What do you think the compiler would do? From the compiler's perspective, what does it do? No, it's not a warning. It's automatic promotion. Okay? You guys never tried something like this in the C class? Okay, how about this? Okay, let's not use the character B. Okay, let's try 0. Okay, how many bytes do you need to store 0? How many bits do you need to store 0? 1 bit, right? So why not? 0 is 0. No. 0 doesn't take 2 bytes. 0 takes 1 byte. Quote, let's see. I'm not sure this won't work. Okay, when you use double quotes, as a string, that will give you a string of a null terminator. Well, plus the terminator itself in C.
I think you have the slash is not correct.
No, that's the right slash. It's a backslash. It's a backslash. It has to be a backslash to escape. And there's a mosquito. It will land on me within 5 minutes. It will. Of all these people in the classroom, it will find me and land on me and suck my blood in 5 minutes. I can guarantee that.
I'll take that action at double or nothing.
Okay, but when you do this, what do you think the compiler would do?
It sets off a section in the memory for 4 bytes because you claimed it as an int.
It will overwrite all the bytes that I has, right? Whether I has 4 bytes or not depends on the platform. If you do this using a 386 architecture, then by default, int is 32-bit. But when you do this using a 64-bit architecture, int by default is actually 64-bit. Okay? But you don't have to take care of anything because the compiler knows how to deal with this. But when you program in assembly, you do not have anything like it. Now in assembly, okay, this is in C. In assembly, what do? in assembly, we can say dot data. This is something that we talked about last time. We have to switch to the data section in order to allocate memory that you will change later on. If you use dot text, you can still allocate memory, but that memory cannot be changed later on. So we switch to dot data, and then you can say I colon, which is equivalent to I equals dot, which is the current counter location of that particular section. And then you can say dot int. And in this case, you have to supply something. You have to say what is the value that you want to initialize I to, which is kind of like I equals 0. In the case of C, it is pre-initialized. Okay? But what is I representing to the assembler? No. It is a label. Okay? All that it is a label. It is a label, in this case, with a value of 0, assuming there are no allocations prior to this. So later on, you can use I basically, just as a label. Now, what if you do something, what if you do something like this? What if you have a MOVB? What is MOVB? Move byte, very good. And what if you say move byte? Let's do something that is entirely incorrect, okay? So we put a 0 here, and then we put a, well, this is not entirely incorrect, but it is incorrect anyway. What do you think this instruction will do?
Copy a 0.
It will copy a 0 to the location starting at the label I. But how many bytes is it copying? Just 1, okay? The compiler would just say, well, that's exactly what you told me to do, because you specify move byte. If you wanted to specify moving 4 bytes, then you have to say move L, or not have the suffix at all, because the implicit suffix is an L. Okay? But the compiler is not going to give you any warning like this. Now, this one doesn't seem too bad. What about the other case? What if I have J here, which is only a byte? Okay, so J, at least to the person reading this code, J is equivalent to a char in C, but that would be the wrong way of looking at things. Okay, if you have something like this and you have move L, move long, how many bytes are we moving when we use move long? 4 bytes at a time. So what if you say move long 0 to J? It will overwrite the 1 byte that you specify here and the following 3 bytes. Now, the following 3 bytes may not even be allocated in the same chunk of code. Maybe you have another dot data section later on to allocate those additional bytes. But you'll be overwriting those 3 additional bytes on top of the byte that you allocate here. Now, maybe the intention was actually to overwrite all 4 bytes. But nonetheless, the assembler is not going to give you any warning. It's not going to say, oh, this is not good because J only has 1 byte. Who says J only has 1 byte? J is nothing more than a label. It is just a location in memory. There's no type, there's no width, there's no size associated with I or J in this case. Okay, so remember that, because if you try to equate this with the C version, which is kind of like char J equals 0 semicolon, then you'll be in for a big surprise, because the assembler does not understand that there are types associated or width associated with the labels. Okay, are there any questions about this? No questions? Okay. Let's go back to the homework assignment, because this example has something to do with the homework assignment. Not a whole lot, just a little bit. Can anyone identify the first operand? What type of operand are we dealing with? Nope. The first one is not direct. The first one is an immediate. Okay? Which means we are not getting the byte pattern from location 0. 0 is the pattern that you want to copy to the second operand. What is the name of the second operand?
I.
I is the expression. What is the type of the second operand?
Direct.
That's direct. Okay, that is our direct operand. Yep.
So should we make label in the homework assignment because you said like don't do anything and it was like.
But there are labels already.
Oh, okay.
Okay, but there are labels in the homework already. You cannot add any additional label definitions. You have to use whatever is supplied. See, I gave you a label, L1, and you have to use L1.
You gave us other labels. What about checkpoint 1?
Hmm?
What about checkpoint 1?
Yep, you can use checkpoint 1 too, except it's not going to be, useful here.
Huh.
Hmm?
Now you've given us a challenge.
This is not a challenge. This one is pretty easy. Okay, well, let's go read this line by line and see if we understand what this assembly code is doing. So I will not hint the solution so that I won't spoil your homework assignment. But at the same time, I will explain it line by line just so that you guys understand the concepts that are involved in this program. Do we understand this line here, dot data? Let me save it and then open it up, using today's folder. So extract to today's folder. At the end of today's class, you can remind me to upload this. But I'm not going to make any changes to it. So I wouldn't worry too much about that. Thank you. That's good. Okay. So here we have, everything in like really, really big font. Do we know what this is doing? We are switching to the data section so that we can start to allocate memory from the data section. What is the difference between the data section and the text section? One is intended for things that you want to change, and the other one is intended for instructions or constants that you don't want to change over time. Okay? Do we understand dot byte? We are allocating byte by byte. How many bytes are we allocating? 4 bytes. Okay, the first byte is hexadecimal 12, the second one is decimal 4, the third one is decimal 63, and the last one is decimal 69. So it will allocate 4 bytes, and each byte have these specific values. Then we have L1 here. L1 is a label. The label is going to be defined to be the same address as the first byte of this part here, dot word. Do we understand what is dot word? Okay, dot word is kind of like dot byte, except each item has 16 bits instead of 8 bits. And then we have tag here, dot ASCII tag in double quotes. So this will basically allocate exactly 4 bytes, and those 4 bytes will be initialized to the ASCII code of uppercase T, lowercase a, and etc. And that's the entire allocation part. This entire part here is to allocate some bytes and have these bytes also initialized to specific values. Then we move on to the text section, which is your code section. We have to say dot global underscore start to quote unquote export the label underscore start, which is the starting point of the entire program. Look at this kind of like main. It's not quite like main, but it is similar to main. It does the same job as main. And underscore start starts here. The first no-op instruction is so that we can put a breakpoint on this very instruction here. And then I put a breakpoint, or I put a label here to stop in my script when I use my script to grade it. And I will check the content of EAX to see if it has the intended value. The intended value of EAX has to be this chunk here, which is in hexadecimal. Okay. So at this point, I have given you just about everything that you need to know, except for one little thing that I have not talked about. If I need to represent an integer using 16 bits or 2 bytes, which byte is going to be the least significant byte? Which byte is going to be the most significant byte? Does everybody understand why there's a question like this? Okay, that is...
Yeah.
Okay. So I'm going to extend the comments here, and I will save the file back into today's folder. Okay. Let's say, okay. This is called the endianness of binary number representation. let's say we want to store the value 0x, oh, I don't know, let's say 62B4, okay? As a hexadecimal number, now I'm hoping that everybody at least know what is a hexadecimal number. Is that okay? Does everybody feel comfortable with base 16 numbers? Okay. So as a base 16 number, how many bytes am I specifying here? Exactly 16 bits, right? Because one digit of a hexadecimal digit represents 4 bits. And we have 4 of those things here, and therefore it will take up exactly 2 bytes. The question is, if I look at the memory, okay, is the bit pattern 0x62 stored in the lower byte, or is the bit pattern 0xb4 stored in the lower byte? Because we have 2 bytes. Now when you have 2 bytes in memory, one has to occupy the lower address and one has to occupy the higher address. Is that good? Because the 386 architecture, just like most architectures today, is byte addressable. In other words, when you specify an address, it is an address of a single byte. In this case, we need 2 bytes to store this particular value. The question is, which bit pattern is going to be stored in the lower address?
What do you mean by lower or higher? It's just like the location?
Yeah, the location. So that's the question. Now there's another way to look at this. The other way to look at this, okay, is this. Okay, so the question is, I know one way to reserve memory is to say dot word 0x62b4, right? If I want to reserve 16 bits and have those 16 bits initialized to 62b4 in base 16, this is one way to do it. That's the easy way to do it. Does everybody agree? Okay. So the question is, can we do the same thing using dot byte 0x62 0xb4 or dot byte 0xb4 0x62? Now, do we understand the question? Okay, the question is, we have dot word 0x62b4, which will reserve exactly 2 bytes, and have those 2 bytes initialized to represent a 16-bit number, which is 62b4 in base 16. That's one way to do it. But I can accomplish exactly the same thing using the dot byte notation, because I can break up the 16-bit bit pattern and just allocate 2 bytes individually. The question is, which way is it? If I go for the first way, then 62 is the one that has the lower address, and B4 is the one that has the higher address. If I do it the second way, then it's just the opposite. B4 has the lower address, and 62 has the higher address. Or if you prefer to spell this out even more, we can spell this out, even more by separating it into 2 lines. Then it is really, really clear which one is the one that has a lower address and which one is the one that has a higher address. Okay, there was a question.
I'm thinking, would you want to specify the B4 first? Because, let's say you're operating on this and you're going sequentially, if you're doing like an addition, the higher numbers would be dependent on the carry to the lower number.
Okay, so your suggestion is to have B4, which is, now is B4 the least significant byte or is it the most significant byte? It is the least significant byte. So your suggestion is to have the least significant byte to consume the lowest address, to use the lower address. And that is correct. That's how the i386 works. Okay, this is what we call a little endian processor, which means the least significant byte takes the lower address. And I will repeat this phrase over and over again because someone is going to make a mistake or forget that later on. Okay. Now, but it also makes sense the opposite way. Okay, there are other processors or protocols that will represent the most significant byte first. Can someone name either a protocol or a processor that uses the big endian standard?
PowerPC.
PowerPC, the Motorola 68000 architecture, the PDP-11, the VAX, which is a successor of the PDP-11. Just about anything that is not Intel uses the big endian notation. Okay, so Intel processors is one of the very few, even though there are more Intel processors out there, but in terms of architectures, there are more architectures using the big endian notation than the little endian, not notation, but standard. But in this class, since we are using the Intel architecture, remember, the least significant byte has the lowest address. That's all that you have to remember. Yep.
Maybe I missed this. Can you clarify, like on your first byte, you have byte 062, and then you have byte 06, or, okay, the bottom example, like you said, you need the B4 before the B62.
Mm-hmm.
So the first byte that's listed is a lower address?
Yes.
You said a low versus high. I'm just trying to conceptualize.
Okay, because this has to do with, pretend that you are the assembler, and you are filling up memory when you see these, dot byte, dot int, dot whatever, structures, right, or instructions. You will see this one first, just because, the assembler reads just like we do, from top to bottom.
Right.
So when you see this first, won't you allocate one byte for B4 first, and then allocate another byte for 6.2?
Right.
That's exactly what I meant by that. So that's why B4, in this case, has the lower address, and 6.2 has the next available address.
Okay, you were calling them low and high at that part.
Low means lower address.
Oh.
But in this case, because when we look at the screen, the one that is allocated first is the one that is higher in terms of line number. Think of line numbers. Okay, whichever allocation has the lower line number has the least significant byte. Okay, so are we okay with this concept? Now, can we write a program to double check and make sure that this is in fact correct? How would I check? Because remember, never trust TAC. Okay, as a general rule of thumb, do not trust test. Do not trust TAC, and you will do fine in this class. If you trust TAC and say, yeah, TAC, whatever TAC says is right, then you will probably fail the class. Why is that?
TAC is often wrong. TAC is often wrong.
TAC is often wrong. Let's make the bold assumption that I'm not always wrong. That I'm usually let's make the assumption that I'm usually right. Okay, even if you know that I'm usually right, according to statistics, you still want to assume that TAC is wrong all the time, because what that does make you do makes you double check everything that I said. Now, how would you double check everything that I said? You don't want to compare to my notes, because I can lie, talking to you, I can lie in my notes too. So what do you want to do?
Internet. Google it.
You can Google it, but the best way to do it is to write a simple program to prove the point. Okay? So you want to design simple, tiny little programs to prove me wrong or right either way. Are you guys getting the idea? So if you want to be successful in this class, the key is to write lots and lots and lots of tiny little programs on every single concept that I talk about in the class. If you can clear away every single concept by writing a simple program to prove me right or prove me wrong, then you should be doing fine in this class. Because you will be doing a lot of little exercises as we go, and you will basically be able to, you won't have as much problem as someone who just says, oh, whatever the note says is right. I don't want to spend the time or the effort to write a simple program to prove that point. So now I'm going to write a program to prove my point. In other words, I'm going to write a program that can prove once and for all to see whether this dot word notation or this dot word allocation is equivalent to these two dot byte allocations. Does everybody understand what I am about to do and why I'm doing it? Okay, so I'm hoping that most of you or many of you will start to think the same way. At the end of a class, when we go to the lab or when you go home, write simple programs. You don't have to write long and complicated programs. Just write simple programs to the point, just to prove one thing exactly. Okay, so here I go writing a simple program to prove either I'm right or I'm wrong. Now, because I'm usually wrong, so I will have to say the point is not to prove me right or prove me wrong. The point is you can prove it one way or another. You have to design experiments that can go one way or another. It has to be conclusive. So I'm going to change to today's folder. Today is 08, and I need the class name as a folder. So everything is going to be in this folder. Just remind me to zip it up and upload it to Moodle at the end of the class. So I'm going to write a program to prove the endianness of the processor or the assembler that we are dealing with. This can be done pretty easily. I have .data here. There are two ways to do it. One way is to use the debugger to help you, and the second way is to actually write some code to prove the point. Let's just go for the first approach, using the debugger first, because you want to learn how to use the debugger. That's how, that's how some of you will be able to, answer or deal with the homework assignment that you have right now. Okay, so the first one is give it a label first. Okay, we'll just call this label 1, and we'll say dot word 0x. What was it again? 62 B4. Okay, and just for convenience, I'm going to use a second label. Okay, I do not really need a second label. I just decided to use it for convenience purposes. So the second one is a dot byte 0xB4 because I am claiming that the Intel architecture is a little endian processor, which means the least significant byte, B4, will have the lower address. Yes? That's pretty much as big as you can go before I run out of space. Sorry? Okay. Okay, so now we allocate for the most significant byte, which is 62, and then we go switch back to dot text. I think we are probably good at this point already. I really don't need anything else. But just to make this program so that it can assemble and we can get into the debugger, we have to give it all this stuff here. Okay. I am not even using L1 or L2 in the program itself. I just want to have the labels so I can examine those memory locations more easily when I use the debugger. I need to make this window.
What were those other 3 lines then? You didn't need them.
Sorry?
What were those other 3 lines then?
Those 3 lines are just for exiting a program correctly.
So I'm guessing it doesn't like it if you leave EAX and EBX?
No, well, if I want to run the program, this will make it terminate at least and not crash. If I don't specify that, it will crash.
Wow, okay.
When are we going to learn those ones?
Sorry?
When are we going to learn those ones?
You will learn it in system surfaces. So we will get to that part. That's how you print too. Okay, so I just assembled the program. And I'm suspecting this is already enough to prove my point. How many of you think that this is already enough to prove my point? Just having assembled the program, not even having linked it or not running GDB. Well, we have a special program called object dump. And object dump can do several things. And of course, I cannot remember all the options. So now I have to look it up and go, do we want to disassemble? Yeah, -D. Okay, so we'll say object dump -D, and the program name is what? endian.o. Nope, it does not show the initialized data section, so that's not good
On
enough.
Thursday you did -D -T.
-D -T, like that. Very good. So this time it showed the allocation, but it did not show the actual data that it will use to initialize those locations. All right, I guess I have to do the LD. I was trying to be lazy. Okay, so now we run the program. Okay, when you run the program, you use L to list the program. And remember, you cannot put a breakpoint on the very first instruction of the entire program. The very first instruction of the program is the one that is right after the underscore start label. So I cannot put a breakpoint here. I can put a breakpoint, but it won't be effective. So the first instruction I can actually stop at is the one on line 11. So I say B11, put a breakpoint there, and just to prove my point, I can run the program, and it stops there. Okay? So now, but you can see the program has nothing to do with L1 or L2. Yep.
Scroll up a little bit to about 4 lines before the top one. A little bit more. I'll see how you.
Well, this is all getting recorded. You can always replay the video clip. Okay. Okay, so the big question now is, how do I examine memory locations? Well, there are a gazillion ways to do it, but most of it, we'll use the X command. We talked about the X command last time too. The help of the X command is just that, okay? X/format, and then you specify an address. That's basically what you do. Okay, address is an expression for the memory address to examine. FMT is a repeat count followed by a format letter and a size letter. Okay, a format letter can be octal, hexadecimal, decimal, unsigned decimal, binary, float, address, instruction, character, and string. Okay, and the size can be B for byte, H for half word, and a half word, interestingly, is 16-bit. A word, in this case, since we're in the debugger, W as word represents 32 bits. Okay, I know it is confusing, but that's the way it is. So you have to remember that. So one thing I can do is to say X/1. Okay, if it is 1, you don't have to type the 1 because implicitly it will just assume it is 1. We want to examine in hexadecimal, and we want to examine a half word for 16-bit. So naturally, we want to say, go to location L1, but this won't work. Okay? No, but remember, never trust tech. So if tech says this won't work, try it anyway. If tech says that thing is going to explode, push the button anyway. Okay, but it says we cannot access it. Okay, there's a reason for that. The reason has to do with GDB is a debugger designed for high-level programming language debugging. So when it looks at a label, it naturally looks at a label as if it is a global integer in C. Now L1 is not a global integer. L1 is an address. So that means when you do something like this, you actually have to do it like ampersand L1. Okay, it does not seem to make sense, but if you think about from the perspective of GDB being designed mostly to work with high-level programming languages, it suddenly starts to make sense, because when the label has no type associated with it, GDB automatically says, oh, if there are no type information associated with the label, I'll just default it. I'll default it to be an integer. Okay? So now it works. The location is this location here, and here we have the bit pattern that we were talking about before. Are we doing okay so far? We got our 16-bit back. But that's natural because L1 was defined using dot word. So it has to work. So since we have L2, we can do the same thing to L2. Aha! L2 is now displayed as one single 16-bit number, exactly the same way as L1. So that proves my point. Yep.
If we go back to the line that says can I access memory at address, it actually gave it away right there. It printed out both the addresses next to each other.
Correct.
Oh, that's wonderful.
Yeah, because GDB automatically associates with the wrong meaning to the label L1. Yep.
Can you explain again the meaning of the 1xh after the x line?
Yes.
What those are, what's those?
Okay, well, the help is still up here. Okay, the first x, which is this x here, is the command itself, is examine.
Right.
The slash is just a separator to separate the command from the format itself. The format is what we call it is a repeat count followed by a format letter and a size letter. In this case, the 1 is a repeat count. How many things do you want to display? And I say one thing. But what is that one thing? That one thing I want to display as hexadecimal. This x here is this x here, which is I want to display as in hexadecimal format, because I can choose to display as decimal if I want to, or unsigned decimal if I want to. But in this case, I want it to be hexadecimal because everything that we have been doing was in hexadecimal. And then the h is the size, which is a half word. A half word is 16-bit. Yep.
So then if you...
Oh, sorry.
So if you want to display like 2 or 3,
You just say 2. Yep. But in fact, we can just do it now. Why don't we do it now just by going back to L1, and instead of asking it to display 1 half word, we want to display 2 half words. Not a problem. Okay, your
Would
question.
it do the same thing if you just did one word?
1W?
Yeah, instead of 2 half words.
Then you have one 32-bit pattern where the least significant 16-bit look exactly the same as the most significant 16-bit. Yep, you can do it. Okay, if I want to show that, but in that case, I only need one of those, and you can see that it's displayed as one single 32-bit integer, where the least significant 16-bit has exactly the same pattern as the most significant 16-bit. Yep.
And that's because you're looking at L1 and L2 together.
Exactly.
Okay.
Yeah, L1 and L2 are nothing more than bookmarks.
Right. But
Okay.
in this example, they just happen to be the same. In some other example, they wouldn't necessarily be the same.
Correct. Yep. Okay. So have I just successfully proven to you several points? One, the Intel architecture is a little endian processor. The least significant byte is the lowest address. Is that good? The second thing is the debugger does not understand types at all. In other words, you have to tell the assembler, or excuse me, you have to tell the debugger how many bytes do you want to display at the same time, and how do you want to interpret those bytes? Do you want to interpret the bytes as a hexadecimal number? Do you want to print it out as a hexadecimal number, or do you want it to be displayed as a decimal number? Are we doing okay so far with this? Yep.
Why do some of them do, Intel does least significant? Why do some do most significant and many?
Well, the choice is somewhat arbitrary because there are good reasons why you want to use big endian as well. Because when you're doing compare, the big endian is easier. When you get the first byte, you can already tell the ordering between two integers. TCP/IP is a protocol that uses big endian. So when you transmit bytes using TCP/IP, the most significant byte is transmitted first.
What about UDP?
UDP, the same thing. The entire IP suite uses a big endian. Now, there's one more thing I want to show you guys, because we have allocated what? How many bytes have we allocated? We have allocated 4 bytes. So one thing you can also do is to display each byte one by one. So you can say 4x, and then you have specified B for 8-bit wide. And we still want to start with L1 because that's the first label. And you can see the actual byte sequence in this case. Okay? So are there any questions right now about the commands that you can use in the debugger? Mm-hmm.
I'm still a little bit confused on like the lower and higher. What you mean by that?
This byte has this byte has the first address, which is at L1. This one is at address L1 plus 1, L1 plus 2, L1 plus 3.
So you want the least significant to be on the bottom?
The least significant byte is the one at the lowest address. Okay. Are there any other questions? No other questions? Do you think what I just did relate to your homework assignment? I just pretty much did the homework assignment. Okay, I show you all the commands that you need to know, and also all the concepts that you need to be aware of when you do the homework assignment. You do not actually need to use the debugger to do the homework assignment. You can just examine how the data is initialized, and you can already tell what to do with the direct operand. Okay, but using the debugger can be very helpful because it can examine memory locations byte by byte. And now that you know the Intel architecture is a little endian architecture, combining that with the ability to display memory byte by byte, that gives you all the tools that you need to do your homework assignment. Okay, are we doing okay so far? Kind of. In terms of concepts, yes, go ahead.
Because as I know, just have the 16 bits for the upward, but then use the 4x byte after the
4xb?
Yeah, 4xb. Why is 4?
4 bytes?
Yep.
I don't have to use 4. I can use 5, 6, whatever. But since we just allocated 4 bytes, it does not make any sense to list more than 4 bytes. Because anything beyond the 4 will be uninitialized. I really don't care what it is because it is not initialized. Yep.
So what if you put the 0x62 and location, the location, like switch locations with that? What would that be?
Switch location? What do you mean?
How you say 0x D4 is got to be on the lower?
Well, you can run the experiment yourself too. I mean, this is all getting recorded, so you can, and also the program is also going to be uploaded. So at the end of the class, I will upload the zip files, and you guys can download the zip file and put it into your virtual machine and run it. Yep.
I still don't understand why in the line before the last one we have 0x62b4, and in the last one.
You mean this line or
yeah,
this line?
No, yeah, this line, and
Uh-huh.
then after the last line we have 0xb4. Like, what was, yeah, how come the switch? Like, I don't get the reason.
Okay. Now remember, we are just examining memory locations with all these commands. Okay, we are not changing anything. We are just examining, memory locations that are now already initialized. Okay. If I want to look at the memory locations byte by byte, I use this command, because this B here means I want to display items by bytes. One item is a byte. I want to display 4 items, 4 bytes, and each byte should be displayed in hexadecimal. This one has the least address. It is at L1. This one is the next byte. It is at L1 plus 1, L1 plus 2, L1 plus 3. Are we doing okay so far with this? This is the memory layout, byte by byte. Okay. If I want to look at all 4 bytes as one single 32-bit integer, okay, how do I look at it? Well, since we already know it is least significant byte at the lowest address, so this means B4 is the least significant byte, and that's why it appears here. The next one is 62, that's why it's here. The next one is B4, that's why it is over here. And then the last one is a 62, which is the most significant byte of the 32-bit when we look at it as a 32-bit quantity. Okay? Yep.
So L1 is pointing to the least significant.
L1 is the address of the first byte that we allocate.
Right.
Okay. Are there any questions? I mean, concept-wise, what are there any questions? Yep.
bits value, then you, and bits to represent some number, you want to allocate the lower bits first up to the higher bits, so you get to know how much bits to begin with. That's what you start out with.
Okay, there's one thing that is important. The way you allocate the bytes has nothing to do with how you want to use the bytes. Okay? Okay, let me show you another example. Maybe another example would be helpful. Okay, so I'll show you another one. We'll call this ndn2.s. Okay, so this one I'll start with one. Okay, let me use L1 here. Let's say we start with one single dot byte. Okay, dot byte 0x56, and then I use a dot word 0x. Doesn't matter. Let's make this a little bit tricky. I will make this 0x5, and then have a dot int 0x. Let's say 6745. Okay. Without even running the debugger, do we know, first of all, how many bytes are allocated here? Well, we just have to add. I mean, we all remember how to add numbers, right? Dot byte is 1 byte. Dot word is 2 bytes, 2, 3. And dot int is 4 bytes. So we are allocating 7 bytes. Do we know from the lowest address to the highest what 7 bytes are actually allocated? Well, let's try to figure that out. Okay, this one is quite obvious. It is allocating exactly 1 byte, and that byte is 0x56. Okay, are there any questions about this? What about this line here? How many bytes are we allocating?
2.
Dot word says we have to allocate 2 bytes. Now, if I want to represent 5 using 2 bytes, and we know this is a little endian processor, what is the first byte? The first byte is 0x05, and the second byte is going to be 0x00. Those are our leading zeros for the 16-bit number. Are we doing okay so far? What about the third line? The third line is, what is the, okay, we're allocating 4 bytes, but we know this is, we are using the convention with the least significant byte first. So the question now is, what is the least significant byte here? 45. Okay, very good. So we have 0x45. What is the next significant byte? 67, but that only accounts for 2 bytes. I need 2 more. Give me 2 more bytes. That's right. Okay, so now, how are we allocating these bytes? Well, the bytes are exactly ordered this way. The 7 bytes that are allocated are exactly in this order of 56, 05, 00, 45, 67, 00, 00. Well, but do you have to interpret those bytes using the boundaries that we use to allocate the bytes? No. Okay? You don't have to do that. Yep.
Yes, I don't understand why we have 0x05, not 0x50, for example.
Sorry?
I don't understand why we have 0x05 and not 0x50.
Because within the byte, we don't change the order.
Okay.
Because within a byte, it is still, okay, there's no ordering question within a byte. In other words, 5 is exactly 05, right? The leading 0 is meaningless. So the 0 here is nothing more than just filling up the space to make it mean 5, but we have to use up 8 bits. Okay, so here's the question. Okay, this is my $2 billion question for you guys. So somewhere in the program here, I say move L. I don't know. Let's say L1 plus. No, L1 is good. Okay. I do something like this. What do you think will be the value of EAX after this instruction? How many people think the assembler will complain and say, excuse me, L1 is a byte, and you cannot do this to a byte? Nobody. Oh, darn it. I was just so hoping I can throw something at someone. Because I just said, do not do it like that. Do not interpret dot byte in the same way as you see it in the C program, right? Okay. So L1 is nothing more than a label that represents an address of a byte somewhere in memory. In this case, it is the 0x56. That's the byte at L1. Okay, so this is going to start with that byte. So first of all, we want to know which 4 bytes are getting moved. Okay, well, we know it starts with this one, but that's only the first one. The next one is this one, the next one is this one, and the last one is this one. Are we convinced that these are the 4 bytes that will be moved? Because we start from L1, and it is a move long instruction. We have to move 32 bits, and therefore we are moving 4 bytes. So these are the 4 bytes getting moved. But when they're moved into EAX and you use the debugger to display the content of EAX, what will be the hexadecimal representation of that number in EAX? In other words, I'm asking you, of these 4 bytes, which one is the most significant byte? 4, 5 is the most significant one. What is the next one?
0.
And the next one is?
5.
And the next one is? That's right. So if you run this program, if you finish a program like this, you run the program, you single step through this instruction, you stop in the next instruction, and you look at EAX using I space R space EAX, you will see 45000556 to be the hexadecimal representation of the bit value of the content of EAX.
If
Yep.
you have another move L to EAX, how is going to change it? Like
If you have
any number, just like move another number to our EAX.
Okay, well, that depends on whether you have the dollar symbol before or not.
Okay.
If you have a dollar sign, well, then it's just whatever the dollar sign specifies.
Oh, okay. It's just gonna
You can even do this to EAX. That'll work. But then EAX becomes the address of the dot byte, the byte that was allocated by the dot byte allocation.
So that would be the beginning of the program.
That will be the beginning of the data section. Yeah, not the entire program, because remember, dot text is somewhere else. So this is the beginning of the dot data section. Yep.
Okay, when you have later one, if we just like declare many of the like, I don't know, we call it like dot byte, dot word, dot int, it's gonna add to label 1. Until
No.
we declare another label.
L1 is just the address of this byte here.
Oh,
Now, those other bytes just turn out to be the bytes after that byte sequentially. Now, no one says that this L1 has to be L1. It can be L1 plus 1. It can be L1 plus 2. Okay, as long as there are enough memory locations to cover what I'm moving, it will still be a predictable move. Yes.
So when you have move L, you're moving along, but if you were to do L1 plus 1, it's still just 1 byte greater than L1?
Well, let's try it. Okay, so I'm going to finish this example with move L1 plus 1, but before I do that, let me answer your question too.
Well, I was just going to ask, what would it do if we tried to move L1 plus
L1 plus
42?
plus 42?
Yeah.
It will okay, I do not know what is the quantum size of memory allocation, but if 42 is out of the smallest unit that the process that the operating system can allocate, then you get a GPF. You get a segmentation fault / a GPF because you'll be accessing memory locations that you're not supposed to. That's a good question. Okay, so we'll just do this one as the last example, okay? Because I have pretty much spelled out your homework, the solution to your homework assignment, after this one. Okay, so let's see, what is the first byte that we are moving here? What is the byte at L1 plus 1? The 05, right? Okay. So here we start with 0, 5, 0, 0, 4, 5, and what is the last one?
6, 7.
Okay, the 6, 7. And of these 4 bytes, which one is the most significant byte? 6, 7, because it has the highest address. Okay, so the number in EAX in hexadecimal representation is going to be 6, 7, 4, 5, 0, 0, 0, 5. Okay. I can say no more because if I say anything else, then the value of the homework assignment is completely evaporating. Are we feeling okay with this? Yep.
Do you want the value of EAX after the checkpoint 1 or before that?
At checkpoint 1.
At checkpoint.
Yeah. In other words, my script is going to place a breakpoint on checkpoint 1, and then the script will also check the value of EAX at that time.
Okay.
Yeah. So it is after the move instruction that you have to change. Mhm. Are there any questions? No questions? Now, if people have any questions about this one, you really need to run it and go to the lab, run this particular sample program and ask me questions in the lab. Okay, because the best way to learn it is interactively. And the debugger, the GDB debugger, is one of the best tools that you can use to learn this kind of stuff. Okay. Shall we move on? Yes? Okay. How many people are feeling a little bit better now about the homework assignment? Okay. There's still one little twist with the homework assignment, but I don't think that twist is really that big of a deal anymore. And 11 people have turned it in. Well, okay, I will take it back. I take it back. 11 people have uploaded something. Which does sometimes it means they know what they're doing, and other times that may not be the case. So sometimes people can upload half-finished programs and just use Moodle as a web storage space, download it back, do it again, continue to work on the homework assignment. Okay, so we are now done with 5.1, 5.2, and 5.3, all the things that you need for your homework assignment. And now we have a digression, which is something that we have already talked about. So I'm not going to do this digression because we just talked about it. Okay. So what you need to do is you still have to read it because, what I just said may not be entirely 100% the same way as I presented here. So you still want to read this particular section, which has to do with the endianness and also the width of the instructions. Okay. Are there any questions about this part? I just explained it in a different way. I mean, that's basically all I did. Okay. Any questions? Hello? Any questions? Okay. Just want to make sure. The next one is indirect addressing mode. How many people do not like pointers in your C class? You'll love this class. Because everything is a pointer. Okay. So let's take a look at the indirect addressing mode because many RISC architectures do not implement the direct addressing mode. In other words, if you're talking about the ARM processor, there's no direct addressing mode. If you're talking about the AVR processor, there's no direct addressing mode. So without the direct addressing mode, how do you access something that is in memory? It seems like that's the only way to access something in memory. Well, we have a better way. It is called the indirect addressing mode. In this case, the value of an indirect addressing mode is the content of a memory location, but the address of that particular memory location is specified by one of the registers. Okay? In other words, you are using a register as a pointer. Now, this is why cisp310 is a prerequisite of this class. Okay? Do you still remember at least the concept of a pointer in C? Okay. Let me just double check, make sure. I can use a text editor for this, so I can just capture everything. Okay. And start with a new document. Okay. In C, I can do something like this. I can say P is a pointer to a character. Okay, do you still remember that? Okay, very good. Can I do something like this? Why not? Exactly, the types are wrong. In other words, in this case, P is a pointer, but I am putting a character into a pointer, which does not make sense. The type does not match. Okay. What if I have a function like this? I have a function f. So I'm making a fairly complete program here. And according to you guys, this is no good, so I'll do this instead. Is that okay?
Yeah.
Well, it's okay as far as the compiler is concerned if you don't enable the compiler to be naggy. If the compiler is naggy, it will actually tell you you are using the pointer before you initialize. Okay? But most of you ignore warnings, right? When the compiler warns you about something, you just say, oh, it's not an error. I can still run the program. Fine, that's good, right? So if you ignore that warning and you run the program, and your program does invoke in a function f here, what's going to happen? Not so good, right? Because what it will do is, as a auto local variable, P is uninitialized. Uninitialized means it is not necessarily 0. Okay, it's just uninitialized. So basically, you're now using a uninitialized 32-bit value as a pointer. This line here will basically say we'll use the content of variable P as an address. At that address, we will store the ASCII code of X. What happens when P is not initialized?
All the bits can be whatever value they orders.
This is really bad because if you are lucky, the program crashes right here. If you're not lucky, what happens? It can crash somewhere else, or the program can just go on because where P is pointing to can be the least significant byte of a 32-bit integer. In other words, you just clobbered the least significant byte of a fairly large number. So for the most part, the program will still run. It is just using the wrong number from that point on. Now, let's just say that this does not crash the program. P is pointing to a local variable somewhere else. Where do you think that P, what the other local variable is at? The caller of this function, the caller of the caller of this function, the caller of the caller of the caller of this function, the caller of the caller of the caller of the caller of this function? Who knows? Right? In other words, by the time the symptom shows up, you would have no idea who clobbered that variable. So this is particularly bad. Now, if you do it wrong and you just say, oh, I'll just initialize everything to null, the program will still crash because you cannot access location 0. But guess what? It crashes exactly where the problem is. So that's a good problem to have. Okay? If you do not initialize it, sometimes it crashes, other times it does not, sometimes it crashes, and sometimes it will keep running, and the symptoms can be different every single time, depending on the test cases that you throw at it. Okay? Okay, so it seems like we do understand the concept of a pointer. But based on that, we already know what is indirect addressing mode. Because when you use indirect addressing mode, this instruction here is basically initializing whatever EAX is pointing to 0. How many bytes am I initializing to 0? Well, look at the suffix of this instruction. One single byte. So I am initializing that one single byte that EAX is pointing to exactly 0. Are we doing okay? So that means that the instruction in section 5.3 can be done by 2 instructions. The first instruction is initializing EAX to the value of label 1. Not the content at label 1, but label 1 itself. In other words, this first instruction will end up initializing EAX to the location where label 1 is defined. The second instruction is going to move 32-bit from 0 to EAX, or where EAX is pointing to. And let me just go back to this section here. This is the code. This is the first version. Oops. This is the second version, but they mean exactly the same thing. Yep. So this means exactly this here. Okay, let me show it side by side so we can see a little better. Come on, resize. There we go. Right there. Well, let's not look at this one first. Let's look at this instruction here. It will crash, but I'm just concerned about the meaning of that instruction. The first operand is $0, which means it's an immediate operand. This one is also moving immediate 0 to somewhere, so that's good. The second operand of this instruction here is a direct addressing mode, or the direct operand. This one without a $ in front of it is a direct operand. What is a direct operand? A direct operand is an expression that gives you a value, an integer value in the end. That integer value becomes the address where, in this case, the 0 is stored. So in this case, the expression is easy. It's just 0. So that means we are going to use 0 as the address of the location that will be the destination of the move instruction. Is that okay so far? Okay. What about in the other case? Well, the first instruction is move L $ label 1 to EAX. Well, I guess they're not exactly the same because this one does not store to label 1. So imagine this is label 1. Okay? So if that is label 1, then the dollar symbol, what is the dollar symbol doing? When the assembler sees the dollar symbol, what do you think the assembler is thinking? Money. No, the assembler is thinking, I am going to see, this is an immediate operand, right? But what exactly is an immediate operand? Whatever the expression after the $ is, that becomes the actual bit pattern to be copied. Okay? In this case, what is the expression right after the $ symbol? Label 1. Okay? Yep, go ahead.
I have a question. Do you always have to have a direct operand followed by a register, like you have a $ and then your value and then comma and %?
No. The only restriction when you use a move instruction, there are two restrictions you have to observe. One we have talked about already, the second one we have not talked about yet. The two restrictions, the first one is the immediate operand can only be the source. Okay, remember that? That one we talked about already. The second restriction we have not talked about is you can only have up to one memory operand. That means you cannot have both operands being direct operands. You cannot say, move B L1, comma L2. That won't work. You can only have up to one memory operand. Other than that, you can have any mixture. Yep.
So you can have less than one memory operand?
Yes, you can move from one register to another register. You can move from immediate to a register. Yep. Yep.
So I was having a little trouble on yesterday, but so when I type in the direct operand, you have move, $, the value, comma, and the value. Is that how I would type it in? Is that how I would change the question mark I would put in? I would take that.
You change the question mark to a direct operand in the homework assignment.
Just like you have it up there, so I would $, and they know.
When you have a $, it is not a direct operand.
Oh, so I use percent sign. And then
No, the percent is the register. You need to read the notes, study a little bit.
Yeah, I studied, but I'm still confused about how to like implement it basically. It's like you know what you're saying, but I don't know how to write it so that it would work.
Okay, well then you want to watch the video clip of today's class, because I pretty much spelled out how you have to do the homework assignment, how you can do the homework assignment using the sample code that I was just using a little bit ago. Okay, so that's a big clue. That's a big clue of how to do the homework. Okay, let's go back to this one here. What exactly is label 1? Well, let's assume that label 1 was defined like this. Okay, so we have label 1 colon dot and 0. So let's make the assumption that label 1 is defined to be the first location of the integer 0 that we are allocating. Okay? In that case, what is label 1? What is the definition of this label 1 here? It is, once again, the address of the first byte of the 4 bytes that we are allocating here. Okay? Is that okay? So what are we actually copying into EAX? The address of the first byte of the .int that we just allocated. Okay? What is the second instruction doing? The second instruction is copying, well, this is an immediate operand again, but this time it's just 0. It's copying a 32-bit 0 to wherever EAX is pointing to. Well, is EAX pointing to some valid memory location? Well, if this is how label 1 is defined, then sure it is pointing to a memory location that can be, yes, go ahead. You guys are all in the same line, so it's kind of hard to point at which one.
So labels are pointers already? Labels are pointers already?
Labels are not pointers. Labels are, once again, they're just symbolic names that can be defined to an integer. That's basically all there is to it. How you use the label can be using it as an address. Okay? So remember that, because there's a fine line between the interpretation. Because when you say a label is an address, that kind of implies that all labels are addresses, or they can all be used as addresses. But that's not the case. Label can be, I can define the label like this, L1 equals 2000. So in this case, L1 is nothing more than the constant 2000. Every time the assembler sees L1, it will say, oh, it's 2000. In this case, every time the assembler sees label 1, it will say, oh, that's the address of the first byte of the .int that you just allocated. So let me answer your question.
I just wanted to make sure I think I forgot the notation. The parents denote the dereferencing, right?
Sorry?
The parents there denote the dereferencing?
The parentheses? Yes. Yes, the parentheses is the indicator that you are using the indirect addressing mode. Yep. Are there any questions at this point? No questions? Okay, well, I'll just kind of finish this up, just to make sure that we have covered, all the necessary components. I cannot read big characters like this. I know it's a lame excuse, but I really cannot read it. Okay, so this one is kind of interesting because when you look at this one single instruction, there's no telling which location is going to be overwritten by 0. Which 4 locations or which one single byte location is going to be reset to 0 because we don't know what EAX is. Is that making any sense? If you just look at one single instruction like this, there's no telling which byte is getting reset or cleared to 0. Because you also have to know the content of EAX at a time. It's just like with the C example, if you use an uninitialized pointer, you don't know whose location is going to get clobbered. Okay? And so that's why, yep, go ahead.
I was just going to ask, so like in a case like that, you'd want to find out what is in that position before
Yes.
you start writing.
Yes, later on in this class, there will be a lot of instructions like this, and many of your programs will crash because you don't have the right content in the registers. So that means every time your program crashes, it will most likely crash in an instruction that has an indirect like addressing mode. So what you need to do when your program crashes is to take a look at all the registers, particularly the one that is being used as the indirect addressing, indirect operand. We are not there yet. I'm just giving you some warnings of the problems that you will see later on, and how what we are talking about now is going to relate to that. Okay. Any questions at this point? What about we just write a program to kind of prove the point? Okay, remember, write simple programs to prove the point. Okay, so I'll just write a program called indirect.s, and I won't even make it complicated. I will just make it so that we have a label L1, and it doesn't do anything except .int is a predefined bit pattern. Okay, and this is just as good as any predefined bit pattern. We'll start with a no op instruction so we can stop before the instruction that we are interested in executes. So the first instruction I will execute is move $L1 to EAX. Well, let's change it. Let's change it so that we can compare between these two instructions. And then the last one is we'll go, let's see, to EBX. Okay. Move L $1, EAX, move L $2, $0, EBX, and like that. Okay, so we'll go ahead and trace this program. Now, every time you write a program to prove a point, to prove tag is right or tag is wrong, what should you do? You should have something in your mind and say, I think this program is going to do this. Okay? So what do you think this program is going to do? Not counting the last three instructions. What do you think is the... Okay, after the first instruction here, what do we expect? Expect... Right? What about the second instruction?
Expect address.
Some address in EAX. What about after the third instruction?
Some address.
Not some address. EBX has the content of that address. Because every time you see register in parentheses, you are dereferencing the pointer. It is almost equivalent to the asterisk symbol in C. Okay? So now that we have some expectations, you can now run the experiment. Now, it is very important not to just run the program and say, oh, this program does this program does that. Okay? It is very important to have your expectation of what the program is going to do. Because it's going to be a useful experience regardless once you have an expectation. Because only two things can happen. One, the program does what you think it does. Okay, that's a good confirmation. My understanding of the concept seems to be right. That's good. But what if the program does not do what you think it does? It's even better. Because it points out that you might have misunderstood something in the class. So you have just caught yourself and say, oh, I thought this is going to do this, but the program actually is doing something else. So now you have to go back to the notes or go to somewhere else, find out what the program actually did and what is your understanding of the program and why was it inconsistent with the actual behavior of the program. So that's why when you run a program like this, you should always come with an expectation of what the program should do, and then you compare the result of the program to your expectations. Yep.
So pretty much that third line then, move one or whatever, is just
Move L for long.
is pretty much saying the content of EAX to EX.
It moves the 4 bytes pointed to by EAX to the register EBX. Okay? Let me say that again. This last instruction, the third instruction of the sequence, this instruction here is going to move whatever EAX point to, the 4 bytes that are pointed to by EAX, to the register EBX. The other way to say that is it will treat the content of EAX as an address. It goes to that particular location, retrieve the 4 bytes at that location, and then copy those 4 bytes to EBX. Okay. So now that we have some expectations, we'll go ahead and assemble and run the program. And we'll GDB run the debugger. Okay. Put a breakpoint on line 7 because we want to put a breakpoint before the first move instruction executes. Okay. Run the program, and this is before the first instruction executes. We really don't need to look at EAX because whatever EAX is at this point is not my doing. It came this way. Okay. We single step the program, we look at EAX again, and sure enough it has the bit pattern of hexadecimal 1, 2, 3, 4, 5, 6, 7, 8, which is expected. So that's good. Now before we run the next instruction, I want to do something. I want to say, print L1 because I want to know what is the address of L1, or that works better. Okay, so now we know L1 as a label is the address hexadecimal 8049090. Are we doing okay so far? And once again, remember that you need the ampersand symbol here because the debugger has a default wrong, incorrect understanding of what L1 represents. Okay? So now we single step the second instruction. In other words, we just executed this instruction here. Now we want to take a look at EAX again. Okay, you can see that this is the address, and EAX has that address. Okay, now before we even run the third instruction, we can actually use the X command, the examine command, to look ahead so that we can expect what is going to be in EBX in the next instruction. In other words, instead of running the next instruction, I can say examine one single thing, display in hexadecimal. It is a word which means 32-bit in the debugger. I just type the entire address, 8049090. Okay, because that will show me what should be copied to EBX in the next instruction. And it is the bit pattern of 010x12345567 Is everything still making sense up to this point? Okay. So now we single step the last instruction of interest. This is the instruction I'm going to execute next. Okay. I look at EBX, and sure enough, EBX now has the bit pattern that we think it should have. Yep.
What does the other number mean?
The other number is the decimal representation of the same value. So this is base 16, this is base 10.
Before you reference the L1, what exactly did that print us? Where's the print L1 so that you're referencing it?
Okay, so we are going back to here. That's exactly 1, 2, 3, 4, 5, 6, 7, 8, but in decimal. Because remember, the debugger thinks L1 is an integer. So when you say print L1, it will automatically interpret it as a 32-bit signed integer. And when you say print L1, it prints it out as a signed integer. You can also specify print /x L1, which will print it out as hexadecimal.
Can we specify something else except
Sorry?
hexadecimal? Can we specify print to specify?
I don't know for sure, so I'm going to ask for help. I mean, I cannot remember every single thing about every single command of GDB. I mean, if I did that, I would have no space left for anything else. My brain would explode. That would not be a good thing. So in this case, you can supply, these are all the options of print. I mean, you can do a lot of stuff. And it takes the same format as X. So that's good. In other words, you can use octal, binary, decimal, unsigned decimal, and so on and so forth. It takes the same format, string, as X itself. So are we doing okay so far with the indirect addressing mode? Okay. Now, if we were using a RISC processor, this would be pretty much the end of all addressing modes. But are we using a RISC processor? No. We are using an Intel processor. And the Intel processor is what we call a cisp processor. So that means we have a lot more addressing modes from this point. I think I just closed the tab that I should not close. So I'm just going to go back to here. Because I want to point out to you guys what you need to read before the next class. And I can tell who has been reading ahead of the class and who has not. Okay, so we are at 5.5 right now. Yes, we're at 5.5 right now. You have to finish the entire section 5 before Thursday. The rest are not really that complicated anymore. They're just basically mixtures of things that we have already talked about. Okay, they look really horrible. Okay, they look really bad, but in terms of concept, they're just combinations of what we have already discussed. And don't forget about the homework assignment. Okay, the homework assignment is due on Thursday before the class.